Welcome to this explainer. Today we're diving into the fundamental engineering tug-of-war between database speed and storage complexity. Look, if you're a systems engineer, you already know the deal. Designing data-intensive applications is rarely about finding some perfect, consequence-free solution. It's almost always a hardcore exercise in mastering trade-offs. So we're going to look right under the hood of the storage and retrieval engines we use every single day. We're going to examine how data actually lives on disk and in memory, and how our absolute, insatiable appetite for lightning-fast query response times forces us to make some pretty significant sacrifices elsewhere in our architecture. Let's get into it.
We're always asking how to make our databases faster. We've all been there, right? A query is lagging, and our very first instinct is usually just to throw an index at the problem. Boom, fixed. But the real question we should be asking as engineers is what that speed actually costs us in system resources. Every single time we optimize for a read, we are implicitly de-optimizing something else. Are we paying for it in write latency? Are we paying in storage amplification? Are we introducing memory overhead that's inevitably going to trigger scaling bottlenecks down the line? Understanding these hidden taxes, well, that's what separates a good systems engineer from a truly great one.
To really ground our discussion, let's look at this core principle of database architecture. Well-chosen indexes speed up read queries, but every index consumes additional disk space and slows down writes. The absolutely crucial takeaway here: there are no silver bullets in system design. Buying read speed always means paying with disk space and write latency. Think about the world's absolute simplest database, a basic append-only file. For writes, it is incredibly fast because you're simply appending data to the tail end of a log. But retrieving a specific record? You have to scan the entire file, which is painfully slow. To fix that read speed, we introduce an index. But maintaining that extra structure incurs overhead. Every single time data is written, the index also has to be updated. So we've successfully sped up our reads, but we've permanently slowed down our writes and bloated our storage footprint.
Okay, here is our technical roadmap for this explainer. 1. The overhead of speed. 2. Unpacking secondary indexes. 3. Clustered storage and heaps. 4. The in-memory revolution. And finally, 5. A summary of trade-offs. Starting off with Section 1, the overhead of speed. Moving right along to Section 2, unpacking secondary indexes.
In any system, we want to find specific data fast. But the database doesn't just magically know where your data is, it has to meticulously maintain a map. While a simple key-value store can easily look up a record by its primary key, modern users want to search by color, or make, or date. And doing that requires a secondary index. This is an index that lets you search by non-primary columns. But here's the catch. Unlike a primary key, a secondary index doesn't uniquely identify a record. If you search for red cars, you don't just get one result. You get hundreds. This non-uniqueness introduces our very first major layer of storage complexity. Because the value isn't unique, the database has to figure out how to efficiently store a single index key that maps to a potentially massive multitude of underlying records. So, to solve this non-uniqueness problem, the database has to construct the index in one of two main ways. Option 1 is to make each value in the index a list of matching row identifiers. If you're familiar with information retrieval, you'll know this as a postings list. So the key red points to an array of IDs, 191, 306, 768, and so on. Option 2 is to make each entry unique by appending a row identifier directly to the index key itself. But in either case, the database is forced to manage this growing, shifting structure. If you update a record's attributes, you have to go in and update the postings list in the secondary index too. This undeniably adds storage overhead and write amplification to your system. Every new secondary index you bolt on is another data structure that must be kept in sync, paid for with your precious write throughput. All right, Section 3, clustered storage and heaps. Let's talk about how this data actually lives on the bare metal of your disk. If the actual data, like the full row or document, is stored directly within the index structure itself, we call that a clustered index. Take MySQL's InnoDB primary key as an example. It keeps everything completely grouped together to maximize retrieval speed. When you query this clustered index, you don't have to follow some pointer to another random location on disk to fetch the rest of the row. The data is just right there. It's the absolute fastest way to read a record based on that specific key. But if you create secondary indexes in this kind of architecture, they don't duplicate the full row. Instead, they store a reference back to the primary key, which means you're doing a double traversal to fetch the actual data.
Conversely, we have the heap file approach. A heap file is a storage method where data is stored in absolutely no particular order, and the index contains direct references to those physical locations on disk. In this model, which databases like Postgres use, the actual rows are essentially just dumped into a giant, unordered pile, which is the heap. The indexes, whether primary or secondary, are kept strictly separate. They stay super lightweight because they only store the key and a direct physical pointer to the specific byte offset in the heap file. When you do an index lookup, the database finds the pointer and then performs a secondary fetch to grab the actual data from the heap.
And I think this brilliantly illustrates the physical trade-off between speed and storage complexity. A clustered index totally avoids that secondary heap fetch to maximize read speed. If your queries are constantly hitting the primary key, it is blazingly fast. But it essentially forces your secondary indexes to rely on resolving the primary key first. On the other hand, a heap file totally levels the playing field. Secondary indexes and primary indexes both just point directly to the heap. The downside? It guarantees that almost every single read will require an extra disk hop to fetch the actual data. If you try to avoid this in a clustered setup by fully embedding the data inside multiple indexes, you end up heavily duplicating data, inflating your storage footprint to absolutely massive proportions.
Which brings us to a really fascinating middle ground, the covering index. A covering index, also known as an index with included columns, stores some of a table's columns directly within the index itself, in addition to storing the full row on the heap or the primary cluster of index. This is huge because it allows specific queries to be answered using the index alone. If a query only asks for columns that are actually present inside the index is said to cover the query. The database never has to resolve the primary key, and it never has to look in the heap file at all. So by using a covering index, you are effectively duplicating specific columns just to buy faster read speeds. It's a highly targeted optimization. You aren't duplicating the entire row, but you are willingly copying data out of the primary storage and into the index structure to prevent that secondary disk fetch. You are deliberately paying the cost in extra disk space and slower writes, because now those duplicated columns must be updated in multiple places whenever a write occurs. It's a calculated compromise, perfectly balancing the read speed extremes of a fully clustered index against the storage efficiency of a lightweight heap pointer. Which brings us to Section 4, the in-memory revolution. So data usually needs to be carefully laid out on disks. Disks are awkward to deal with, sure, but they're incredibly cheap and durable. But what happens when we break the disk barrier entirely? Well, as RAM has become cheaper, keeping entire datasets in memory has become highly feasible, and that's led to the massive rise of in-memory databases like VoltDB or SingleStore. Now, to survive the volatility of RAM, because obviously RAM wipes on power loss, these systems use a few clever techniques. They might use specialized hardware, like battery-powered RAM, but more commonly they ensure durability by asynchronously writing an append-only log of changes to a persistent disk, taking periodic snapshots, or replicating the in-memory state to other machines over the network. When they restart, they simply reload their state. The disk essentially just becomes a backup plan. The reads are always served blazing fast, entirely from RAM.
Now, this is actually my favorite part, because there is a totally counterintuitive truth about why in-memory databases are actually faster. You might logically assume it's simply because they don't have to wait for a physical disk to spin or an SSD to return data, right? Well, that's not the whole story. Even a traditional disk-based storage engine may literally never need to read from disk if you have enough memory, because the operating system heavily caches recently used disk blocks in RAM anyway. The true speed advantage of in-memory databases actually comes from avoiding the heavy CPU overhead of encoding data. Think about it. Traditional databases must constantly translate in-memory data structures into a dense, serialized byte format that can be written safely to a disk block. By completely stripping away that serialization tax, in-memory databases unlock blistering speeds, but at the cost of highly expensive RAM infrastructure.
Let's bring it all home in Section 5, Summary of Trade-offs. Synthesizing everything we've covered today, it's pretty clear that every single architectural layer forces a deliberate choice between read latency, write performance, and storage amplification. If you add secondary indexes, your reads definitely get much faster, but your writes slow down, and your storage complexity rises to a medium level as you start managing postings lists. If you leverage clustered indexes, your reads on that specific index are the absolute fastest because there's no heap fetch, but your storage complexity shoots up to high if you start duplicating data across multiple indexes. Covering indexes offer a really solid middle ground. faster reads by answering queries directly, but they still slow down writes and create medium to high storage complexity through that partial data duplication. And finally, in-memory databases give you blazing fast reads and fast writes, but the storage complexity is incredibly high because you are paying a premium for RAM while still having to manage those disk-based durability logs in the background. Knowing that there is absolutely no perfect solution and that speed always exacts a heavy toll in storage or write latency, you are left with an engineering absolute. You simply cannot have it all. You have to ask yourself, which constraint can your specific application actually afford? Are you going to sacrifice your write throughput for lightning-fast reads? Will you just eat the cost of massive storage amplification to cover your queries? Or will you pay the financial premium for in-memory processing? The choice is entirely yours, but the bill always comes due. Thank you for joining me on this explainer, and I will see you in the next one.